Hi class. In this video we're going to be talking about exact equations. And usually these will be a little bit more involved on the calculus side because we're going to have to take both derivatives and antiderivatives. I'm going to start off with just number 1. We have y e to the xy plus cosine x dx plus x e to the xy dy equals 0. And I once got this piece of advice from a calculus teacher. If it looks horrible, it's probably exact. Unfortunately, we can't count on probably, so we have to actually check that this thing is exact. We recall that the thing multiplying dx is called m, and the thing multiplying dy is called n, and we need to check dm dy, the derivative of m with respect to y, and compare that to the derivative of n with respect to x. If these two quantities are the same, the equation is exact and we can continue. Okay, so let's see. dm dy is the derivative with respect to y of y e to the xy plus cosine x. So this means that y is the variable that's moving and x is treated as a constant. So here I'm going to have to do the product rule. I get e to the xy plus xy e to the xy plus 0, because the derivative of with respect to y of cosine of x, that's just a constant now, so the derivative with respect to y is just 0. Meanwhile, when we check dn dx, we hold y constant and let x move around, and we can see what's going to happen is that we're going to do the product rule again. If I take the derivative of x with respect to x, I get 1 times e to the xy. Now if I take the derivative of e to the xy with respect to x, I get y, and then x e to the xy. But these terms are the same, so it is exact. And we should be excited, because we can actually solve it. Okay, well what we do from here is to say the solution, so not only do we know it's exact, we know what the solution should look like. I'm looking for f of xy, and the solution of the differential equation will just be f of xy equals a constant equals c. But f of xy is just given by the integral of, in our case, you can choose either one you want, but I'm going to integrate m with respect to x, or we could integrate n with respect to y. It doesn't really matter which one you choose. You won't be able to duck out of any complicated integrals. Oops, doesn't need to be read. Y is being held fixed here, so I have y e to the xy over y plus sine x. And now my constant of integration will no longer just be a regular constant, but a function of y. So what I have, if I simplify y over y, is just 1. So f of xy is this function which depends on an arbitrary function of y. I need to figure out what g of y is. Once I do that, I'll have f of xy, and then I'll have my solution to the differential equation. To isolate g of y, what we check is df dy is supposed to be n. So I need to find d dy of e to the xy plus sine x plus g of y, and I need to set that equal to n, which is x e to the xy. This will generate an equation in terms of actually g prime of y, as we're about to see. So when I take the derivative here, I get x e to the xy plus 0, because the sine of x, the derivative with respect to y of sine x is 0, since that's a constant. Notice I have x e to the xy on both sides, so I can cancel them, and I get g prime of y equals 0. Well, if g prime of y equals 0, this means that g of y, it's a y, is a constant. Since I already have an arbitrary constant floating around, my solution looks like f of xy equals c reduces to e to the xy plus sine x equals c. I can combine the constant from g of y and my constant in the solution already into a single arbitrary constant, and this is my solution. Okay, let's try another one. Let's try number 8. 8 reads 1 plus natural log of x over y dx minus x log x over y squared dy equals 0. And I'm going to try to, I know I'm going to need some space, so I'm going to try to keep everything over here. M is the thing multiplying dx. So dm dy is, well, the top is just a constant, and I have 1 plus log x. The derivative of 1 over y is negative y to the negative 2. That's actually it, because the 1 plus log x is a constant with respect to y. dn dx, well, notice I have a minus in there. That's actually going to come out front. I'm going to rewrite it as negative y to the negative 2. And then I get to do the product rule on the inside. Taking the derivative of x yields 1, so I get log x plus x over x, which is 1. And notice that these terms are the same, so it is exact. By the way, what happens if it's not exact? Well, this solution technique doesn't work at all. That's what happens. Okay, so now what we do is we start finding f of xy. It's the integral of m dx, which is the integral of 1 plus log x over y dx. The 1 over y comes out as a multiplier. I have x plus integral log x dx, because the integral of 1 dx is pretty easy. And now, to do this integral, I need to integrate by parts. I'm going to write that in red, because I think it writes a little smaller. The most complicated thing that I know how to integrate in this expression is dx, where v is just x. That leaves u as log x, and so du is dx over x. When I do the integration by parts formula, I get x log x minus integral dx. So we get 1 over y times x plus x log x minus x plus g of y. Notice I can simplify. Minus x and x cancel. So what I have, I'm going to write up here a little bigger. F of xy is x log x over y plus g of y. And now, using the fact that df dy equals n tells me that d dy of the expression that I just found, x log x over y plus g of y, should equal negative x log x over y squared. over y squared, sorry. Taking the derivative on the left-hand side, x log x is just a constant, and then I get negative y to the negative 2 plus g prime of y equals negative x log n, negative x ln of x over y squared. Notice that these are just different ways to write the same thing. So I get g prime of y is 0, which tells us that g of y is a constant, just as before. Okay, well, if g of y is a constant, when I put it in here, I know that the solution, f of xy equals c, is reduced to x log x over y equals a constant. And that's it. So even though these seem miserably hard, they're not as long as they're exact and you're solid on your differentiation and your integration techniques. As you may imagine, these are the main sticking points for students. Remembering your integration and your differentiation and integration rules.